morning, everybody. We were looking at wind power as one of the potential renewable energy sources to try and plug the gap for our energy needs by the end of the year, based on the fact that fossil fuels are potentially going to run out by the middle of this century, or not long after. We'll calculate that lifetime in the next lecture. We're going to be using wind power, as we did in the last lecture, as an example, focusing on the UK, which is well placed to utilise wind power, and the European Union, before scaling up to the globe to see what the potential is for global contribution of wind power in a practical sense. So we got to about 2014, looking at the evolution of wind power installation in Europe. And by the end of 2014, there was around about 129 gigawatts of installed wind energy capacity. That's capacity, so that's potentially what could be utilised provided everything works to its maximum. And in 2014, that capacity was split between about 121 gigawatts onshore and about 8 gigawatts offshore. And that relative contribution has been changing slowly over the last 5 years. But by 2014, there was around about 11,800 megawatts of wind power capacity in the European Union. And if we compare that to the previous year, 2013, that was an increase of about 3.8%. So that's roughly the sort of increase in terms of installation capacity that's been going on. It's fluctuated, obviously. And the EU power sector basically decided more than a decade ago that it should move away from fossil fuels, fuel oil, coal and gas, and each of those technologies, some more than others, continue to be commissioned more than they install. So we have to find a way to replace those. And the wind power capacity installed, it says now, but that was in 2014, would typically produce about 284 terawatt hours of electricity. That was enough to power, or rather cover, about 10% or so of the EU's then current electricity consumption. Technology improves. We think about building even bigger turbines. This is one of the biggest ones you can get today. This is built in Germany, and it's a 6,000 kilowatt nominal power turbine with a rotor diameter of 126 meters. Obviously you can't build quite so many of those in a given space. But that's the sort of technological development that's been ongoing over the last 5 years. So what about offshore wind power? We said that potentially that might be of more, that might actually contribute a lot more, provided we can get access to relatively shallow waters to build these things economically. Now, offshore winds are going to be stronger and steadier on land. Obviously, it's much smoother, the sea surface generally. So that means effectively that provided the wind blows for a long period of time, you can generate essentially more power per unit area than, say, an onshore wind farm on average. And actually, one of the first wind farms built in the UK was the so-called Kentish Flats wind farm. It's actually built about 8.5 kilometres out into the Thames estuary. And that started operation at the end of 2005. And that's a good example, historically, to compare current growth rates against. And it was predicted then to have an average power per unit area of around about 3.2 watts per metre squared. Remember, we estimated about 2 watts per metre squared for onshore wind farms. Did it achieve that? Well, at the end of 2006, its average power per unit area actually was 2.6 watts per metre squared, about 80% of the predicted value. But of course, that's going to fluctuate depending upon the average wind speed per year. So, in going forward then, let's assume that a power per unit area for an offshore wind farm is about 3 watts per metre squared, 50% more than an onshore wind farm. Okay? And remember, this is for the UK. Now, it turns out that British territorial waters, the shallow waters, 25 to 50 metres deep, 30 metres deep I should say, cover an area of about 40,000 square kilometres. So potentially that's what we can make use of. Mostly it's off the coast of England and Wales. And the average power available, if we were to utilise everything at that power density, would be around about 120 gigawatts. That's equivalent to about 48 kilowatt hours per day per person in the UK, assuming we can utilise that entire area, which of course we can't. So that's assumed for various reasons we can only make use of, say, about a third of that area. It's still a pretty big area. In other words, a third of 48 kilowatts per person per day, kilowatt hours per person per day, is about 16. So that's what we potentially might make use of. But remember, that's an area 2/3 the size of the country of Wales. Let's think about putting these power turbines all the way around the coastline of the UK. The UK has a coastline length of around about 3,000 kilometres. Let's imagine we put a line of turbines 4 kilometres deep all the way around the UK. That's roughly an area of almost 13,000 square kilometres, taking into account the curvature. So effectively 1/3 roughly of our 40,000, we're getting to around about 16 kilowatt hours per day per person. So that's the area we needed to deliver that amount of power per hour per day per person for the UK. Is that practical? Well, how many turbines would we need to deliver 16 kilowatt hours per day per person using that power density of 3 watts per metre squared? Well, we would need, let's assume that the turbines are 3 megawatt nominal turbines, which is an average. We would need 44,000 turbines. 44,000 turbines. That's about 15 kilometres. So I beg your pardon, that's about 15 turbines per kilometre placed around the entire length of the UK coastline, assuming they're evenly spaced, of course. Now, of course, there are lots of practical problems you have to think about. For example, offshore wind utilisation is very hard on machinery. Sea salt environments are very corrosive. That means that the equipment requires expensive and constant maintenance. A good example would be one of the first wind farms in Europe, which was the so-called Horns Reef wind farm, which was built off the coast of Denmark, relatively small, about 80 turbines. After 18 months of exposure to sea air, the entire wind farm had to be dismantled and repaired. We look at the Kentish Flats wind farm in the Thames Estuary. That had similar problems to their gearboxes. After 18 months, about a third needed replacement during the first 18 months of operation. So there are these additional expenses and issues that need to be addressed compared to other types of energy generation. What if we were to try and make use of deeper waters? And again, the UK is pretty well placed. Our UK territorial waters with depths between 25 and 50 metres is actually about 80,000 square kilometres. So let's do a little thought experiment and assume that we have this area about the size of Scotland available for wind power. If we assume our 3 watts per metre squared, then we could build deep offshore wind farms which could deliver up to 240 gigawatts, 96 kilowatt hours per day per person. Again, we would have to fill that complete area with turbines. But let's assume we've got to make room for shipping, etc. Let's assume we can only make use of about a third of that total area. In other words, we end up with an area about 30% bigger than Wales. And again, if we were to build a strip 9 kilometres wide all around the coast in these deep offshore regions, we could perhaps deliver 32 kilowatt hours per day per person, which sounds pretty big. It's a huge amount of power, but it's still nowhere near our current consumption. When this written, it was just over 100 kilowatt hours per day, but if we include things like transport, etc., remember one of our previous graphs showed, on average, the UK consumes about 128 kilowatt hours per day per person. So it's a relatively small but significant fraction if we could build wind farms over that large area. But at the time, offshore wind farms were considered quite expensive, although that's changing. And there are a few other things that we tend to forget about as well. If we wanted to produce 48 kilowatt hours per day per person for the UK, that would require 60 million tonnes of concrete and steel. 60 million tonnes. That's 1 tonne per person. By comparison, in about 2015, the global steel production was about 1,200 million tonnes. That's about 0.2 tonnes per person in the whole world. Making that many turbines would be a huge feat. And that would be a construction on a scale not seen, certainly in the UK, Europe, since the Second World War, or the Golden Era. Now, for comparison, if we wanted to make, say, 48 kilowatt hours per day per person using nuclear power, we would need 8 million tonnes of steel and 0.14 million tonnes of concrete. So you can see the difference there. What about gas? Well, and oil. Well, currently there are about 7,000 kilometres of pipelines in UK waters in the North Sea. That's composed of 8 million tonnes of steel and concrete. And the recently completed and in use Langeland gas pipeline all the way from Norway to Britain, which provides gas with a power potential of 25 gigawatts, that's about 10 kilowatt hours per day per person. That used an extra 1 million tonnes of steel and 1 million tonnes of concrete. So it is doable, but it's expensive and it's going to take time. So in 2007, the UK government actually allowed creation of 33 gigawatts of offshore wind capacity and gave permission to build these. And in theory, that would deliver on average about 10 gigawatts of power to the UK, or 4.4 kilowatt hours per day per person on average, if we think about the whole of the UK. Let's assume a figure of 4 kilowatt hour per day per person can be achieved if we build those wind farms. Well, they were built. To obtain that average power, we require 10,000 3 megawatt wind turbines. We could build bigger ones, and a few of them. Now, they have a capacity of 3 megawatts, but on average, they would typically only generate about 1 megawatt, because the wind is not steady, and we've got maintenance issues, etc., to think about. So the question is, what would that 33 gigawatt cost to erect? Well, obviously, the economics are going to change rapidly with time, but if we compare the cost to the biggest one previously in the UK, which was the Kentish Flats in the Thames Estuary, that actually cost £105 million, and that was only 90 megawatts. So 33 gigawatts, if we were to simply scale up, would cost about £33 billion, or £550 per person in the UK, using figures from then. If we wanted to erect 10,000 wind turbines to get our 33 gigawatts, say taking a period of 10 years, which is what it was estimated it would take, that would require also some rather large commitment in terms of capital investment for these so-called jack-up barges, and you need 50 of them. These are the things that carry these huge turbines out into the sea and erect them. Those then cost £60 million each. So you need an extra £3 billion just to get all those wind turbines on site. Now, our Dutch colleagues were quite pleased with this because they're the ones who actually build those barges. But you can see the things you have to think about when we put together these renewable wind farms, renewable energy wind farms. Let's wind forward to 2015, and the government again approved the world's largest offshore wind farm, and that was off the northeast coast of the UK, off the coast of Hull. It's around about 130 kilometres off the coast. And I remember up until then the largest wind farm was the London Array offshore wind farm, which was an extension of the one we previously talked about. It was about 630 megawatts. But this new one, called the Dogger Bank Creek Beck A and Dogger Bank Creek B wind projects, which is being constructed now, that would hopefully have 400 turbines, and it would generate about 2.4 gigawatts, so significantly larger, 4 times as large as the previous largest one, and that would provide power to about 2 million households. Not all their power, but that would be the contribution to the number of households. So offshore wind farm installations have been increasing steadily, and the question is, where are we now? Well, remember the UK is one of the most favourable locations for wind power in the Northern Hemisphere, probably the best in Europe because of its coastline and shallow waters. In 2015, wind power contributed about 11% of the UK electricity generation. That rose to about 17% in 2016-17, then 19.3% in 2018. And by comparison, in 2018, it together with other renewables such as hydro, etc., and biomass burning, contributed almost a third of the UK's electricity. So wind power continued to provide a growing percentage of the energy for the United Kingdom. For example, in March 2016, there was about 6,700 wind turbines with a total installed capacity of around about 13.5 gigawatts. And the balance between onshore and offshore is shown here, 8,500 or so megawatts of onshore versus only about 5,000 megawatts of offshore capacity. But that ratio has been changing. And in 2016, the UK was ranked as the world's 6th largest producer of wind power in terms of total. And it actually contributed significantly more compared to all the other renewable energy sources in the UK, as you can see here, offshore, onshore, etc., etc. These figures are actually for 2017-18. But you can see, based on these more recent figures in terms of the installed capacity in gigawatts, there's been a slow increase in onshore and in particular offshore wind capacity compared to some of the others. So the question is, how far can we go? Where are we now in terms of perhaps say global energy from wind energy? Well, the capacity of all wind turbines installed worldwide at the end of 2017 reached about 540,000 megawatts. Wind turbines installed by the end of 2017, if you do the sums, could actually contribute 5% of the total world energy demand. 5%. So you can see we're a long way short in terms of, on average, of our 5Q by the end of the century. Now, that may be true on average, but remember, many countries are very well placed to make use of wind power, and so wind power has become central to their strategies to phase out fossil fuels, particularly smaller countries. For example, in 2017, Denmark, which has a long history of building and using wind turbine farms, that set a new world record of 43% of its power coming from wind. And an increasing number of countries have reached double-digit wind power share, including Germany, Ireland, Portugal, Spain, Sweden, and Uruguay. And again, by the end of 2017, this was the total installed wind power capacity, and you can see the UK has now moved up to 5th place. Now, in Europe, some of the relative increases in installed capacity for wind power has started to decline slightly. As you can see from this graph here, the growth rates have declined. That's partly due to economics, partly due to effectively some areas running out of space, some countries running out of space for installing new capacity. And it takes a bit longer to install offshore capacity. But you can see there's been a gradual increase, certainly across Europe, between 2013 and 2017, of around about 10%. And if we look at the annual megawatts and the cumulative megawatts based on the installed and under construction or those wind farms in early or advanced planning, you see we're heading for around about 35,000 cumulative megawatts installation by 2020. So the global increase is continuing. But the question is that going to be enough to fill our energy needs by the end of the century? Obviously not, based on the numbers you've seen so far. The other thing to remember is that while the onshore wind market is larger globally in terms of total megawatt plant capacity, offshore is slowly growing. In fact, the growth rate of offshore wind farm installation is actually increasing. It's now usually around about 10-11%, whereas the onshore wind farm growth rate is less than 10%. So by 2018, wind power reached around about 600 gigawatts globally, with about 54 gigawatts added in 2018. China leads with more than 200 gigawatts, USA, lots of land area, mainly onshore wind farms, 100 gigawatts. Europe was a bit in decline, but that's on average. For example, in the UK, September 18, a new wind farm was approved called the Walney Extension, and that's the largest offshore wind farm in the world, 660 megawatts, and that will be providing electricity to 600,000 homes. And then there's another one currently under construction, which will double that, the so-called Hornsea wind farm, 1,200 megawatts. So the UK is continuing to increase its electricity capacity from wind. And if we just step back and compare what the situation was in 2005 to 2017, so the wind up here is in dark blue, you see that the contribution or the share of installed electrical power capacity is about 6% for wind, or 41 gigawatts, whereas in 2017 it had risen up to 18%. So these figures are for Europe, 18% on average. So that's a very large increase over about 12 years. Compare that to those other contributions to the electricity capacity market. You can see effectively that solar has increased rapidly from 0.3% to 11.5%. Again, certain countries in Europe are more favourably placed to make use of solar, such as Spain, southern France, southern Germany, but that's increased to around about 11.5%. And if you look at those graphs carefully, you can see that we're approaching around about half of that pie chart is contributed to by these renewables: hydroelectric, biomass burning, other, wind and solar. And you can see that the wind energy increase and solar energy increase has been at the expense mainly of coal and fuel oil. Nuclear has gone down significantly as well, but you have to be careful. That's partly due to decommissioning of various power plants. And of course more of those may come online in future as well, as we'll see. So, that's the situation in Europe. And just to show you how wind power has compared against all the other sources of wind electric power generation, nuclear, gas, solar, coal, fuel oil, large hydro and biomass, you can see that gradually it's overtaken fuel oil, then it's overtaken nuclear, then it's overtaken hydroelectric, and then coal. But of course, still the biggest contributor is gas, and that seems to have resisted any change, as you saw from the previous pie charts. Gas has essentially remained relatively constant in terms of its contribution. So, what is the total contribution to EU electrical power, if somebody asks you? Well, 2016 at the end of it was around 11.6%, and that had risen to just over 18% by the end of 2017. So we're looking at roughly 20% in terms of wind power's contribution to our electricity needs in Europe. Right, it's a lot of numbers to try and take in, so let's have a short intermission. And if you're old enough, you might remember when early in the 2000s, when a lot of these wind power farms were being proposed, there was a lot of objections to them for some of the reasons we discussed. But one of the more interesting ones, for example, was that the environmental lobbies said that they would end up killing lots of wild birds. And interestingly, in Denmark, who have a long history of wind turbines, they actually counted and collected all the birds that were killed by wind turbines, the birds that fly into the rotors and obviously killed, unfortunately. So they knew how many birds were killed per year from so many wind turbines. So if you were to scale that up to the UK, as the environmentalist lobby did, which is fair enough, they said it would kill around about 30,000 wild birds per year. That sounds like a large number. But let's put that into context. And this is discussed by Mackay in his book Sustainable Energy Without the Hot Air. In the same period, 1 million wild birds were killed by motor cars. So should we ban motor cars? But even that number pales into insignificance compared to the number one killer of wild birds in the UK. 55 million. Does anybody know what the number one killer of birds is in the UK? Pet cats. So try and maintain equilibrium, so to speak, in a lot of these arguments and look at the facts. Anyway, that's our intermission. Let's continue. What about wind power going forward on a global scale? How many Q per year realistically do you think we can make use of? Well, unfortunately that's not easy because wind power does vary quite a lot, as we showed from the previous survey maps. So let's split onshore and offshore sites separately between 2 and 4 watts per metre squared, as we've discussed. Let's look at land-based wind power first. Now, we looked at the United States, which is obviously very favourably placed because of its large land area to make use of land-based wind power. Let's make a bottom-up estimate for inland areas, assuming we can transfer the US experience to the globe. The electrical power consumption in the United States in 2017 was about 0.01 Q per year. It's actually 0.008 Q per year, but let's round it up to 0.01 Q per year. Let's assume that all of that can be supplied by wind energy, and the rest of the world, on average, is about as well placed as the US, which it won't be, but let's assume it is, for utilising that wind energy resource. Then, as the US is about, say, 1/17 of the world's land area, that gives us 0.17 Q per year, assuming the 0.01 Q for the US is accurate. We can also produce a top-down estimate. So we said in our original budget analysis that 12 Q per year are required to drive the atmospheric wind system. 30% of the world's land area is the world's surface is land. And we said that in general the wind speeds over land are much lower than over the sea on average. So let's say we shouldn't allow more than 15% of the total for around about 1.8 Q per year as an absolute upper limit. So again, our estimates of 1.8 Q per year and 0.17 are within a factor of 10. And as we said before, if we have a collection efficiency of 10%, we're doing pretty well in terms of accessing the energy available. Let's take the lower limit for, again, our S2, our ultimate capacity of 0.17 Q per year. What about offshore? Well, let's look at this previous survey and try and restrict ourselves to continental shelves, obviously. Let's make a rough estimate of those shelf areas, waters less than 50 metres deep. And if we look at the offshore winds in terms of wind speed, or in terms of their mean wind speed, based on, say, 3 watts per metre squared, let's compare it to, say, our exercise when we looked at the Orkney island power density of 9 megawatts per kilometre squared. Let's use that. Well, that would yield about 0.12 Q per year. But then remember, practically not more than about 20% of that is likely to be exploitable. So we can take the final value of S2 for both onshore and offshore as 0.2 Q per year. Is 0.2 Q per year a big or small number compared to our estimated 3 to 5 Q per year needed by the end of the century? It's a small contribution. It might be very significant for certain countries, but not globally. So we have to think carefully about the so-called energy gap that we're going to have to try and plug with other sources. Okay. So let's continue by looking at some of the other potential renewable energy sources. And what we're going to do is look at a particular renewable energy source where people spend a lot of time and energy looking at designing ways of accessing it and retrieving energy from one of these pathways we discussed in our energy budget. And this is actually going to serve as a warning. It's an exercise, but it serves as a warning about things may look good to start with, but in practice they end up not generating what we think they're going to generate. So this is just to get you to think a little bit. And we're going to think about wave power. Now, obviously as the wind blows over the ocean, it generates waves. And those waves obviously contain energy. So the question is, can we extract energy from waves, from water waves? So we're going to do a simple bottom-up approach again and see if we can extract an equation for the amount of energy that can be produced by water waves. And again, as before, we're going to have to work out the average power per unit, whatever it is that waves have. In this case, we're going to look at the average power per unit length of the wave. And we're going to assume that that energy is going to be delivered to somewhere near a coastline where we can build something that can extract that energy. Let's assume that the group velocity of our water wave is given by that equation, 1/2 root g lambda over 2 pi, which is a fairly common equation. Lambda is the wavelength, as shown in the bottom right diagram of the wave. G acceleration due to gravity. So we can calculate the energy associated with that wave by simply multiplying mgh by 1/2, where in this case h is the amplitude of the wave and m is the mass contained within the wave, in this case of water. So we can calculate the energy per unit area of our wave. It's simply 1/2 rho gh squared, where rho in this case is the density of water. So our power per unit length, and we're thinking now about per unit length of coastline, where we might actually extract that energy, where all the energy is going to be dissipated hopefully, is simply F is equal to U times C. U, remember, is the energy per unit area, C is the group velocity here. So F is simply given by this equation. And let's put some real numbers in there. Let's say we have an amplitude for our water wave of 1.5 meters. Wavelength might be, say, 10 meters. So then we're estimating a value for F of around about 23 kilowatts per meter. That looks pretty good. How realistic is it? Well, let's remember that in open water, waves are generated when wind speeds get above about 0.5 meter per second. The wavelength of the waves will change, in other words, the distance between the crests, and the period actually depends on the speed of the wind. So the higher the wind speed, the greater the period generally. And the longer the wind blows for, and the greater the expanse over which that wind blows, means you get bigger and bigger waves. Now it turns out that the prevailing winds, of course, over the Atlantic are from west to east, and the waves arriving on the Atlantic coast of Europe are very big, certainly much larger compared to the waves, for example, in the North Sea that arrive on the east coast of the British Isles, which are much smaller on average. So we have to think a little bit about putting an upper bound on the maximum power based on the typical height of the waves, etc. So the upper bound with the maximum power that could be obtained can be estimated if we know what the incoming power per unit length is for some exposed coastline and simply multiplying by the length of coastline. So we're simply trying to work out the amount of energy coming into our exposed coastline. Turns out that people have actually gone into the Atlantic and measured the amount of power in Atlantic waves, and it turns out to be around about 40 kilowatt per meter of exposed coastline. A bit bigger than our previous estimate of 23 kilowatts per meter. So again, that looks pretty good. Now, if everyone in the UK owned a meter of coastline and could harness the whole 40 kilowatts, that would be a lot of power for them to cover a lot of their modern consumption needs. But our population is too big, 65 million or so. There's not enough Atlantic-facing coastline for everyone to have their own meter of wave. In fact, this is what the typical picture looks like. We have about 1,000 kilometers of Atlantic coastline, 750 to the north, 250 to the south. Ireland has a bit in the middle. So the total raw, so I beg your pardon, that 1,000 kilometre equates to about 1/60th of a metre per person. So that reduces our amount of power significantly that we can access. So the total raw incoming power is now down to 16 kilowatt hours per day per person. Sounds a little bit like wind energy, if you remember. So if we were able to extract all of that power, just like our wind turbines, it basically means that the sea behind these lines, where we're going to assume we can extract that wave power, would be completely flat. Obviously that's not going to happen. Again, we have to think about the efficiency of whatever our wave electricity generator system can achieve. Because remember, some of the power is going to be lost during conversion from that mechanical energy into electricity. Let's assume we can make some magical wave generator that's 50% efficient. And let's suppose we were able to place them along half of that length we see there, 500 kilometres, facing the Atlantic. That will deliver about 25% of this theoretical upper bound. So in other words, a quarter of 16, about 4 kilowatt hours per day per person. Even that's optimistic. So you see our numbers coming down and down and down. The question is, do such generators exist? Well, yes, they were actually invented by Richard Yem and Professor Stephen Salter at the University of Edinburgh. And again, this is a bit of an old report, but they actually built 3 of those wave machines and they installed them. In fact, they installed them off the coast of Portugal, and they're in the process of building even bigger wave generating machines, which were going to be installed off Orkney, which is a good place for wave machines. However, they didn't publish any performance results from their ocean tests, but the makers claimed that a 2-kilometre long wave farm consisting of 40 so-called sea snake generators, we'll see a picture in a minute, was able to deliver 6 kilowatts per metre of wave farm. Okay, well, if we use that 6 kilowatts per metre of wave farm in our previous calculation, then we can calculate the power delivered over 500 kilometres of wave farm. It's actually only 1.2 kilowatt hours per day per person. That's not very much. Remember, 40 watts is 1 kilowatt hour per day. So, the assumption was that wave power could be useful to small communities on remote islands, such as the Orkneys, but it won't play a significant role in certainly Britain's sustainable energy problem. And that's a picture of what these sea snakes look like. So big hinged tubes, 120 metre long, 3.5 metre diameter, and as they flex, they effectively pumped through these hydraulic capacitors fluid through an electrical generator. And the peak power, it was claimed from one generator, was about 750 kilowatts. So in the best Atlantic location, wave height, wavelength, the average power was around about 300 kilowatts. These were called the Polaris wave energy collectors. And it was proposed that 13 of those, providing 10 megawatts, could be installed off the northern coast of Scotland, actually off the coast of Shetland rather than Orkney. It changed from 2015 to 16. So the question is, did this happen? Well, while you're thinking about that, let's see if we can scale up using a thought experiment this type of energy collection to the globe. Let's do it for the whole of the North Atlantic and look at the estimated power input. Let's assume that there's no energy lost or dissipated due to breaking waves in the middle of the Atlantic, which is not correct. Let's assume all the energy is going to be dissipated at the coastline. How can we calculate that? Well, first thing to remember is we're assuming that the input power is going to be the power delivered to the coast of the entire Atlantic, North Atlantic. Let's assume that the North Atlantic Ocean is a circle of radius, say, 2,000 kilometres. Then the input power, W, is simply the coastline length, if you like, the circumference, times our previous F. So that gives us about 2.9 times 10 to the 11 watts. And the power per unit area, there's a little bit of a problem here, but let's assume it's a flat circle. It's simply that W divided by pi r squared which gives us about 0.023 watts per meter squared, so very, very small. We can then make an estimate using that number of the total worldwide annual energy input to the Earth. Remember, the world oceans cover about just under 3/4 of the world's surface, 0.7 say. So the total wave power area is 0.7 times 4 pi r squared, whereas the radius of the Earth, remember we're looking at a sphere, radius of the Earth is 6,360 kilometers. Put those numbers into the equation. The area of the ocean is approximately 3.5 times 10 to the 13 meters, based on our very simple calculation here. If you do it properly and add up all the surface area, you actually get to a figure that's actually quite close, 3.6 times 10 to the 13, so good estimate. So the total power is equal to the area times the power, the unit area input. That gives us around about 8.1 times 10 to the 11 watts. In other words, that's 0.024 cube per year. Pretty small. Now again, it depends on which area you use. If you were to use pi r squared instead of 4 pi r squared, it's 0.06 cube per year. But again, it's a very, very small number. So it's not looking as though it's going to be terribly practical. But people made estimates about where the best locations might be, just as for wind and solar power, and those are the best locations. And you can see they're in the far northern hemisphere and the far southern hemisphere, where wave motion tends to be greater due to the fact that we have higher wind speeds across the ocean. And look at the numbers there. You're typically looking at below 5 kilowatts per meter, maybe 50 to 60 kilowatt per meter around northern UK and Iceland, for example. However, the company which was in the process of trying to build these power plants went bust, and they are now no more, because effectively their numbers didn't really add up, as you can see from the previous calculations. So a lot of effort went into trying to build these renewable energy resources, but basically the economics and the maximum power output at the end of the day was not sufficient to make them viable. Okay, so that's that unfortunate story. What we'll do is we'll continue tomorrow by looking at other renewable energy sources such as tidal power and solar power. So we'll start again tomorrow. So thank you very much for coming. See you tomorrow.